Great. It's great to see so many people here at the Geoscience, our first official meeting as a special interest group. This one. Okay. Give myself 10 minutes for the introduction, and we've used 5 getting everyone in the room, so this will be very quick. We've got a quick agenda. The agendas are all on the sheets of paper on the table in front of you as well. So after last year's RSCCon, where we had our first sort of geoscience, we actually called it weather and climate meeting, but we had a vote to change the name to Geoscience. We formed a special interest committee. The chair is myself, Helen Burns, and Deputy Isabel. Give us a wave, Isabel. And then we've got a whole host of wider committee members. If you guys could raise your hand if you're in the room. Yeah, so there you go. These guys helped put all the session together. So a bit of housekeeping. We've set up a Slack channel for this session. This might be especially helpful for the remote participants as the Zoom chat is disabled. But if you want to stay in contact or chat about the session, please feel free to use this Slack channel. All the questions will be taken via the conference Slido. So please use the conference Slido for questions. There's links to those on your table, and we'll keep displaying links to it on the during this presentation. We've also created a hack pad, which we'll be using to give your feedback later for breakout groups. In the hack pad, this is linked to in the abstract, and it's linked on on QR codes and on this presentation as well. So it's on your sheets of paper on the table. And this contains all the links you'll need for this session, including the Slido links to Mentimeter, and links to our website. Yeah, so just a general thing, please be considerate of others when using the hackpad and Slido, because they're community things. And for the discussions, we've got a microphone here that should pick up this area of the room. And we're hoping we've got an owl over in that area of the room that should pick up people in that area. Fingers crossed. Bit of trial and error with that. But please, remote participants, if you don't hear a question during the discussion, please let us know via the Slack channel, and we'll get people to repeat their question. Okay, so we're going to start with a little bit of polling to get to know who's in the room. So if I can get you all to scan this QR codes or follow the link on your sheets of paper. Give you a second to get this loaded. I'll load it on my phone. See people getting there. Still see a few people scanning. Do you want me to share the screen to get the results on that? I think, will it appear? Yeah, actually, yeah, maybe do that. So I stop sharing. I've got that. Are you on it, or shall I bring it? So I think most people have answered by now. Yes, you can see a whole host of different backgrounds there. So many of you from physics. Great, yeah, so that's interesting. A lot of people coming from wider backgrounds than the Earth and Earth, Ocean, weather sciences. Okay, let's move on to the next question. current domain area. Quite a wide uh, spectrum of disciplines there, but a lot of you from weather, climate, oceanography, atmospheric science, like myself. Okay, next slide. All right, welcome. You're an expert in. Yeah, probably don't try and write a huge. Yeah, so we've got lots of expertise in a wide range of stuff in the room. Hopefully, yeah, we can share all this knowledge. I think that's most of the answers coming in. We move on to the next. Okay, and what is something you're interested in and would like to learn? Great, so yeah, a real mix of people wanting to learn more about their domain area and more about technical um, RSC type topics. Okay, and next slide, I don't know if there's any more. Oh, there's another one. And where do you get your main funding? I imagine there's only going to be a few of these. It doesn't surprise me very much to see that a lot of people's main funding source is NEC, which is great because we've got a speaker from NEC talking later in this afternoon session. Okay, so I think that's all of the polling done now. So hopefully we'll use some of your answers here to inform some of our discussion later. And I'm running slightly over, so Isabel, if I get you to stop sharing your screen. Okay, just in case you've not found it, the links for today that's the RSC, main RSC Slido. We're track D, and that's the link to the hackpad. Again, if you don't catch these now, they are printed out on your tables. A few more things. Okay, so now hang on. Okay, now we're going to move on to our keynote from Brian Lawrence. Brian is a professor at Reading University who does research in both computer science and meteorology. as well as handling a lot of the delivery of advanced computing to NCAS. And oh yeah, I'll let Brian come up and yeah, talk.
I'm just sticking in presentation mode. I'm good to go. Cool.
Great.
Very good. Thank you. Okay. Very nice to have an invitation to be here, and I was completely bamboozled as to what to talk about. So what I thought I'd talk about is some of the activities of what is, I think, the oldest university research software engineering group in the UK. Certainly, if not the oldest, one of the oldest in size and breadth of activities. And clearly we need some context. So I'm going to try and do that in 15 or so minutes with a few subliminal slides. So I want to start by talking about climate modelling, and I'll get to why I don't want to talk about weather today, although my job title is both weather and climate. And really, climate modelling is a huge consumer of computing and producer of data. And no matter how much computing we have, we will always want more. And in the context, kind of for some of you who are not in this field, give you some idea of why that is in terms of resolution, complexity, and ensembles. And then a little touch on the group we've got at Reading and what they do, and then some example activities, and basically across from modelling at scale to data. And I suspect I'll run out of time, so I'll give a bit subliminal, but I'll make the slides public, and most of the projects are public anyway. So I'm sure most of you know this, but climate models consist of lots and lots of grid boxes that talk to each other, and you can have millions of grid boxes, hundreds of variables, and you're trying to measure the state of these things, changing the state every few minutes for years, if not centuries. And if you multiply up the powers of 10 a few times, you suddenly discover why we need big HPC. That's it. And inside each grid box, we have lots of processes, and then the grid boxes might be organised in interesting ways. And for this talk, I don't want to talk about the interesting ways, except to point out that if you want to compare the simulations from two models and they're on different interesting grids, then you have a data handling problem. Okay. So if people give you more compute, we like to use it, but we like to use it in different ways. We can use it by increasing the complexity, have more processes, more things going on in every grid cell. We can spend it on resolution. We can have just more grid cells. We can spend it on ensemble size. That means more simulations. Or we can spend it on doing more fun things with data. And for any given problem, it's a different mix of things that one needs to use. And so, for example, in a climate model, you will have all sorts of processes dealing with chemistry, the land surface, the ocean, the clouds, aerosols, and all of these things have to be managed over time. And so you're looking at the change of state of these things, and often you're interested in diagnostic processes, which you might not want to predict from one step to another, but you still might want to write them out every now and again, what's gone on in a grid cell. So there's not, you have to worry about not only the data that you're moving around or keeping track of, but all the other things you might want to know about that's going on in the model when you're dealing with data, hence huge producers of data. The land surface, for example, is we're always evolving things. There's lots going on. You've got in any given cell, you then worry about all the different kinds of things that are on the land surface in the cell and what's going on in terms of the exchanges with the atmosphere and so on. So there's all of this complexity. So we want, if you give me more computing, I'd like to have more complexity. On the other hand, if you talk about resolution, I try and give you a serial idea of what resolution actually means in a climate model. On the top left, the box, this is New Zealand, because it's got good orography for this talk, so good mountains. So on the top left, that's the standard climate model resolution that the IPCC main simulations are run at. And then going around, we see more and more resolution. And you can see that the islands get better resolved. You start to see mountains, and it's quite important that actually, as you go to higher resolution, the mountains get higher. So, and particularly if you're interested in extremes and what's going on in terms of climate, then you then you need to worry quite a lot about getting to the highest possible resolution. But I can't have really high resolution and long runs and big ensembles, hence all of the choices. But if I do have high resolution, I get to see what's going on much better in terms of the processes and the impacts in those extremes. So here's two different simulations of the same event at low resolution on the left and high resolution on the right. And you can see, even without looking at worrying too much about what the colours mean, you can see that everything's much better resolved. If you really want to know what's going on, you want to be at high resolution. The other really key thing is an ensemble. So a large ensemble where we typically want sort of 20, 30, 40 members, each of which are essentially trying to do the same projection of the future and try and understand the natural variability in the system, that despite however you might be forcing it in terms of expected climate forcings. So variability really matters at regional scale. So coming back to saying something useful about climate at the regional scale, we need large ensembles, but they can't be at high resolution, they can't be that complex. But a particular large concept of a large ensemble is that we try really hard to have the same experimental protocol and only sample it internal variability. And that's going to matter because one of our examples is going to be about that. So we worry about essentially 4 coupled model systems at the moment. Ones that are designed to run centennial simulations down to ones where we're really trying to look at extremes in future climate. And so that table's going down in resolution. So at the top, we've got the 100-kilometre ones that were at the top left, and on the bottom, we've got 10-kilometre model resolutions that were down towards the bottom right of that example I gave you. Give you an idea of the sorts of things they're doing. They're running at about simulating sort of between 0.5 and 5 simulated years per day, depending on the resolution. So that's per real day, and they're generating terabytes of data per real day, and so we're managing petabytes of data. And I always say that I think the worst thing about SI units is that petabytes has the same number of syllables and the same number of letters as kilobytes, and it's a hugely different problem. And gigabytes, even terabytes, that extra factor of 1,000 just makes life very, very difficult. So at the top, we've got, as I say, the standard centennial. I'm going to talk to you a little bit about the next one down, which is our large ensemble resolution, and a little bit about what we're trying to do with a new version of the next one down. And I'm not going to talk at all about the last one because we're building this now, aiming to make it as a coupled system. We've got an atmosphere and an ocean, but coupling the system turns out to be a little bit harder. So from the point of view of the people who have to do this, the RSE group that are managing all of this, we're trying to run these models on Archer 2, and we're trying to get the data to Jasmine, and we're trying to do a lot of things. We have to build the model, there has to be post-processing. We will see shortly that we're resubmitting the model over and over again and managing that. And so there's an awful lot of things done by the Computational Model Services group at MCAS Reading. And so I'm not going to go through the gory details of that, but the key take-home point is lots and lots of things, lots of infrastructure, managing this virtual computer called Puma 2 that sits inside Archer 2, which orchestrates a lot of what goes on. And so the group handling that is tolerably large, depending on how much extra money we've got at any given time, sort of around 10 to 15 people. And most people do a bit of everything, but we have data handling as a speciality, workflow, HPC, deep HPC, and then the applications, and lots of people involved. And run a help desk, actually it's been quite quiet lately. I just had a look, so it's very quiet usually over August. Nobody does anything in August apparently, and then we get lots and lots of queries in September and October as things pick up. So, but basically anyone in the UK who's trying to run a climate model can generate queries, and clearly you have local RSE support. Many of you are here, but we kind of expect people to participate in Met Office models that will help them in some way or another if they need that help, particularly on the national platforms and sometimes on their own platforms. Okay, so the examples. to tell you a little bit about Canary. Canary is a large cross-NERC centre project looking at climate change in the Arctic and North Atlantic. And for this, we've run one of these large ensembles. And what does running a large ensemble entails? It entails running a lot of historical experiments from 1850 to 1950 to get us some initial conditions. And then we run 40 historical simulations from 1950 to 2014 in this case, and then 40 more simulations from there to 2100. And so if you do the maths, you'll work out that's 6,000 years of simulation of a very high resolution model, or relatively high resolution model. And there are lots of people involved in that. And a lot of people had to put it together. So this is what I want to tell you about a little bit, that putting a modelling program together like this takes a large chunk of people. Not everybody in that there is in the CMS group, but most of them are. And there's a whole range of tasks that were required to happen to put this together. It took us well over a year to build the model and the IO and all the systems that were necessary to actually do this, despite the fact we started with a model that ran. So, yeah, it's just hard logistically to make this sort of thing work. And then another bunch of people had to run the model, keep the thing in the machine, because and that's the take-home point there. But if you look at the graph on the bottom left, this is this model status per day. If you look at the time axis, we had these 40 members in Archer 2 for well over a year. So we were running simulations, and you can see up to 60 tasks at a time running in the machine, because things would break and we'd have to resubmit, and we ran them in 3-month cycles, hence that orchestration we were talking about before. So that orchestration is just resubmitting the 3 months, and then the humans have to get involved because something goes wrong. Those of you who use Archer 2 know that something goes wrong on a regular basis, and they have to get involved and deal with it. And so you know, the idea that we run a model at a particular speed is a laughable idea. On the right-hand side, you see the actual speeds in simulated years per day, and you can see that the average speed was a little over 2 simulated years per day, but we had all sorts of other things going on as well. Right, okay, so, and of course that generated data. So we have the 6,000 years of simulation. Each of those generated 822 atomic data sets, that's particular variables, and we had restarts and all sorts of other gubbins. We used a petabyte of disk as cache, and we generated 5.5 petabytes of data. So again, easy to say, enormously difficult to manage. And so there's real challenge at that scale. And I didn't highlight it when I introduced Canary, but we're also trying to nest higher resolution models for particular incidents. And so here, for example, it's just some results from one of these nests. We're trying to look at a storm at even higher resolution. Right, okay, quickly jumping on. How much time have I got left?
3 minutes.
3 minutes, cool. Okay, so another thing we're doing is porting to Grace Hopper. So Grace Hopper, some of you will know, is a complicated beast. It's got a Grace CPU and a GPU next to it, and the nodes come with 4 of these things on it, and we would ask ourselves, can we get a coupled model on that platform? Well, we think so, and we want to, because Jupiter's just being deployed in Germany. We've got ALPS available. We're working on ALPS right now in Switzerland, and one day we might be able to access to Isambard AI for more than just playing. And we think we can get one of these simulations running where we simultaneously run the atmosphere on the Grace CPU and the ocean on the GPU. But this, we think, will take us about 6 months to a year of 4 people working more or less full-time to make it happen. That's the scale of what we're trying to do here. A German colleague's estimated it cost them €1 million to do a port like this. That's just hard yakka. Right. Okay, 2 more quick ones. One more about models and data. So there's a project running, led by, amongst other people, Luke Abraham, and involving, Sadie's pictures disappeared off, but Sadie in the background, working on the fact that what we also obviously have to do is compare models with data, and we also have to help people decide where they want to fly the aircraft to make measurements. So this kind of interaction of models and data requires new toolkits. So an interesting project building those toolkits, and building them out of standards. basically standards-based activities. A lot of what we do is standards-based. So this uses the Vision toolkit. Oh, there's Sadie's picture. I knew it was there somewhere. Built on CF Python and CF Plot, which are Python packages which respect the standards and allow us to manipulate data in a far easier way. And finally, because I've run out of time, I'm sure, I just wanted to say one thing about boring low-level HDF5 or NetCDF4. Many of you will have been using that data. We've just released a version of a package called Pi5, which is a pure Python HDF5 and NetCDF4 reader. And that's a game changer for lots of reasons. Those of you who think you have to use ZAR because you're on your object store, you don't. You can keep using HDF5 because we have a pure Python solution to this now, and it's relatively efficient. And if you're using Ka-chunk or whatever, you also don't need to do that anymore. And we're in the process of putting it in the back ends of all the major projects. And a byproduct of this is most of us are obviously quite worried about what's going on in the US right now. And HDF5, of course, is a package that's maintained by a US company, which effectively depends on US government income. And we should all be worried about that. And we've all got petabytes of HDF5 and NetCDF4 data, but it's okay because we now have something that's not maintained by the Americans. And I'll leave it there.
That right, and it's amazing. 26 slides in 15 minutes. Like something. Okay, so I'm going to bring up the Slido if I can find it. Here we go. Okay, so our first question is, if you could have double resolution or an ensemble at an eighth of the current resolution, which would you choose and for what applications?
Oh, the second clause is the giveaway. I would choose both of them depending on the application. Although to be fair, 8 is quite a small ensemble size. If you're interested in variability at the kind of regional level, it's probably a sensible size for a centennial scale simulation where you don't have much choice. So I would choose both. Double the more I want to look at extremes, the higher the resolution. The more I want to look at regional scales, the bigger the ensemble.
More questions. I might be really not naughty then and ask you a quick question, not through Slido because I'm struggling to get it on time. So it's clear that MCAS CMS is like really needed and really helpful. How much of a challenge, do you know, was it getting it funded in the first place before you could demonstrate how needed it was?
Those of you who've got access to the slide deck will see that the slide I didn't show you, the last one, is our funding mix. Historically, we oh, there you go. You can hold it up if you want. Oh yeah, I did have a summary slide, but I skipped that. Yeah, so roughly half our income is NCAS National Capability Funding from NERC. Sustaining that in the current environment is tough. So the more people say we're useful, the better. And we clearly are trying to get funding from as many different sources as we possibly can, diversification being.
There's another question on Slido now.
Okay. Can you explain what makes you think the jump needed?
So I was desperate for someone to ask that. So one of the reasons ZAR was created was because people could not deal. Well, there are several reasons. Let's start with the C libraries at the basis of HDF5 are basically not thread safe, so you can't parallelize things as well as you would like. So if you use ZAR, you don't go through a C library, and so you can parallelize things really well. So now we've got Pi5, that excuse is gone. Another reason is it's actually tolerably inefficient sometimes if you've got a very complex file because of the way that chunking works in HDF files. But you can get around that. Again, there's details in the slides. And I can't remember the third reason. The third reason on the slide too. They tell you when you do media courses, never ever say, I'm going to tell you 3 things because you'll forget the third. That's truth.
Okay, and you've got 1 minute to answer the last
Yes.
question. Can Pi5
Yes.
use as a backend?
So right now, H5 NetCDF, which is a pure Python package, is being re-engineered for Pi5, and I think the pull requests went through last week. So it hasn't quite been accepted, I think, but well, it might have been because we're waiting on. There's another one coming for enumeration support, and then we'll be done, and it'll be an H5 NetCDF. So yes.
Great. Thank you very much. I might get you to answer the last question on the Slack. We need to move on. Yes, so any questions missed will either be answered in the discussion or on the Slack channel. Okay.
Okay, we've got the lightning talks next, and we will go just in the order like they idea. So if you're on with a lightning talk, try to identify your presentation here, and you know at what point you will be on. So our first speaker is Henry.
Yeah.
Yes, Henry, about Iris.
Yep. Thank you very much. Let me know when I run out of time if I do.
I will.
Thank you. Yeah, so I'm from the Met Office. I'm with my colleague Stephen, waving now in the room. Yeah, we are not in the same. Well, yeah, there's lots of other people from the Met Office, but we specifically two are from a specific team called the AVD team, which stands for Analysis and Visualization of Data. Within our team, this is our sort of core motto. So we sort of enable users to focus on science through the provision of standard scientific tooling, support, and best practice. This comes in the form of, we develop open source Python packages. We provide a scientific software stack for our users to use to make it easier for them to have environments. And then we also support those users all the time through in-person and online support. So our software, so we have a lot of different libraries. They're all on GitHub, they're all open source. They're all in this open source organization called SciTools. They're just to run through a couple. So we have Iris, this is our sort of flagship package, and we'll talk more about that one in a minute. CarterPy, this is sort of, we're a bit more hands-off with this one, but this is based on matplotlib, and is a great graphing tool. Tephi is for tephigrams. GeoVista is our sort of one of our newer things, and that's for 3D meshes and unstructured data, and that one's really cool. So yeah, these are all open source on our GitHub, and yeah, many more. This is not an exhaustive list. Iris, so Iris, you can see by the description, but a powerful format agnostic and community-driven Python package for analyzing and visualizing Earth science data. There are 4 sort of points I wanted to bring up about Iris. Obviously, I can't go into everything, and there's more to all of this stuff, but interoperability is really big with Iris. We have Pandas interoperability. We have some interoperability with some of our other packages, such as GeoVista, for example. We'll touch on NC data later, which is a bridge between Iris and X-ray. So yeah, we love interoperability, and we're really keen to have more of that. The CF conventions, so Iris treats NetCDF files and their metadata by the CF conventions. So we sort of expect certain things from your files, and that allows us to do more cool things. We do try to be as open-minded as possible, and even if you're not CF compliant, do the best we can to help you get there with Iris. But yeah, that's about that. Multiprocessing, so Iris uses Dask under the hood, and we try and it's all Python API, so we don't ask you to actually touch the Dask under the hood, and we let you use some of Iris's conveniences to configure that under the hood. Yeah, unstructured data. So Iris is also, we've had a lot of time looking at UGrid and unstructured data. So that's cool. Recent Iris highlights. I'm not going to go into detail about all of these things, but if any of these things are interesting to you, come and talk to us. yeah, and then the future things that we're looking at to be working on as we're always developing new features and taking requests for features and what our users want. NC data, so I mentioned this earlier. This allows you to interact with X-ray and turn X-ray objects into iris cubes, as we call them. But this means that if you're a primarily X-ray user, but like the idea of a feature that we talk about in Iris, you can transfer over, use the Iris feature, and then transfer back, and your files will stay essentially the same. You can also fix files and use this to like adjust them. I'm just cautious of my time, so I'm going quickly. But Iris ESMF regrid, so this builds on top of the regridding that is already in Iris. It uses ESMPy and scipy.sparse under the hood, but it's still Python native. All of our API is Python. You don't need to know any of that sort of stuff, but it approximates latitudes from great circles. It has unstructured support. It's mainly unstructured support and UGrid and all of that. And then one of the big things working on with this is partition support, because there's a memory bottleneck in ESMPy. Last slide, essentially, open source management. We have lots of repositories, we have lots of users making requests, and we have to manage all this stuff. I'm running out of time, it seems, so I'm not going to go into any of this. But if you're interested in any of this, please come and talk to us or reach out on GitHub. That is it.
Thank you very much.
Thank you.
We'll have a discussion after this. If you have a question for Henry, please prefix your question on Slido with his name, and the same for all of our other speakers. Okay, who's the next person? Matt. About attempting to uni-FHAI methodological modeling.
Right, actually, on a project that I've got involved in, which is essentially developing a. And better microphone too. Essentially developing or attempting to develop a modeling framework for people in hydrology mainly. It started as, although I think it has grander ambitions, but which one? That one. The idea, the acronym is expanded at the top. If you're wondering where that came from, but the idea came out of essentially a bunch of hydrologists who were fed up with the way hydrological modeling was working, and you've seen how complicated modeling can be from Brian's talk. Well, hydrology has slightly smaller models, but it definitely has other problems in terms of the variety of models we have. They all don't necessarily work independently of each other, or they don't talk to each other. It has their own little silos and their own very preferred models, and it's very frustrating if you actually want to do proper science. I think was the argument. So the idea that came out of this was to, I think, I got involved in this at a later stage, but I think the initial idea was to build a framework that allows all these different models to work together, and then sort of achieve that by splitting the hydrological cycle, the water cycle, essentially up into different components, which could, and then the idea being that the model had to fit this component, but it could do what it liked, so long as it produced and accepted the mandatory or subset of the mandatory transfers between each of the areas of the cycle. That's what the pink arrow is for. Now, the great thing about modeling frameworks and integrated modeling frameworks is that it sounds great in principle, but it's very complicated. This is a genuine picture of me trying to work out something. Please don't actually try and work out what's going on there. It's not necessary. It just illustrates the complications behind these things and the amount of learning that I had to do being brought into this project to understand what was going on and what was needed to be done. So I'm sort of doing this showing this as a, I wouldn't say a cry for help, but I'm always interested in how other people are doing these things. Everyone has different ideas when it comes to modeling frameworks. I've seen lots of different approaches to it. All of them seem quite complicated under the hood, but I'm keen to learn more, basically. And one of the big drivers behind this project is a model called JAWS, which is the land surface model, which Brian mentioned earlier. So the land surface, the bottom bit of the climate models, which in itself is quite a fearsome beast. It's unnecessarily complicated and very difficult to use. So there's a big project, a separate part of the project that's trying to move this into this framework to make it easier to use. However, at this stage, I would argue that the framework is actually not particularly wonderfully well used at the moment because it has a lot of issues. So yes, it works, but only with a lot of specific tweaks and workarounds. And so what I'm hoping to do over the next few months, could end up being years, is to actually make this software that someone has put a lot of effort into developing actually something that people will want to, or scientists will want to use. At the moment, it has a lot of issues with it's not particularly fast, which is difficult when we're doing high resolution modeling. There's a parallelization question in there at the moment. It doesn't do that. It's all running in serial. It needs a lot of improvements in the area of data compatibility. So it's very, very fussy about what it accepts. And there was another issue, and there was the rule of 3 again, and I forgot to put it up, and I've forgotten what it is. But that will do for now. So I'm interested in talking about integrated modeling and modeling frameworks and that sort of thing, and happy to take ideas and questions and all the rest of it. There you go.
Thank you. Again, yeah. Any questions? These prefix with Matt. And we've got Esther talking about. Do I go to this a PDF? It's just it's nice. A data science platform demo.
Cool, I'm Esther. I'm here with Colin to talk about some infrastructure work that we're doing at the National Oceanography Centre, which I will abbreviate to NOC. And I do have to say this is sort of a shortened version of a talk that we're doing later today. So if you're interested, we can absolutely talk about it now, but also come to track A at 4:30. Oh, that does do every slide at once. Okay. So why are we building a data science platform? Give you a bit of a sort of wider context around some of the work that's going on here. NOC is undergoing a digital transformation, so that means that we are investing in digital skills, infrastructure, artificial intelligence and machine learning capabilities, and external partnerships. And our work building a data science platform is an underpinning part of this. We're trying to make it easier for our researchers to access compute and to have a uniform way of accessing different types of compute, using it to support that training in digital skills. And it provides a route to access accelerated hardware, both for AI, ML, but also just for people who want to run code that is designed to run on GPUs. So our initial audience is the sort of 400 researchers at NOC. We are also trying to sort of go forward and make this a bit more external, but the NOC researchers are sort of the first. And we have been running a test deployment of this platform for the last year, gradually roping more and more people in to test it. We have about 100 people registered to use it at the moment. So what is it? What am I even talking about? We're really talking about a Jupyter Hub-based platform where we provide environments, sort of pre-configured environments that suit most of our users' needs, so that the average person can just log in and they don't have to worry about installing things. They can do it through a web browser. They can do it with pre-existing NOC credentials. They don't have to install anything on their laptop. And then we're also, so our test instance is deployed on premises on servers at NOC. We're borrowing a couple of servers, old servers from an old project. They're not lovely, high spec, but they're fine for our test purposes. We're trying to buy new hardware And we're also currently working on deploying it with various cloud providers to open it up to a wider audience. So we have stripped back our data science platform in order to put it on my binder. No, I want to connect. So I did launch this just before the session, so hopefully it won't take too long. So this is a stripped back version of the platform, but just to give you an idea. So we've taken out a lot of the software dependencies. We've taken out our MATLAB integration because obviously our license isn't valid to use on my binder. But you know, it's a fairly standard Jupyter type platform. You can open up your notebooks. So obviously this is Python. We also support R and sort of Julia, and yeah, MATLAB, and people can open up MATLAB in a web browser through this as well. You have your terminal. Really popular with our researchers is being able to use remote desktops on this in order to connect to the existing NOC servers. Classically at NOC we use no machine. People have to install a client on their own laptop, and then it's a bit laggy. The resolution's not great. We've had some really positive feedback about an alternate. This is, by the way, this is the remote desktop. It is a really basic. We do, in fact, offer a selection of ones. Yeah, so I think like really, really brief tour, but yeah, that's pretty much it. I'm very happy to talk more. Colin is also very happy to talk more. I will volunteer him, but we will be talking more about it later. Anyway, I don't where did the slides go? There. Cool.
Thank you. Okay, let's see. Joe. Hi, Joe. I guess. Yeah, as well. Are you happy for the spread this way?
Yeah, that's fine. Thank you. Yeah, I thought, thank you for the opportunity to talk here. I'm just going to do lightning talk on accelerating UKCA by predicting time steps with FTorch, and I'll explain what UKCA and FTorch are throughout the talk. This is work with Jack, who's in the room, and then also Luke Abraham at Cambridge, who was mentioned in one of the other talks. So yeah, Luke is the code owner of UKCA, and UKCA is the chemistry and aerosol code that's used both by the Met Office and also in the UK Earth System model. It covers quite a wide range of different chemical species. So you can, depending on the configuration, it's got like between 85 and 200 chemical species being modeled in the atmosphere, and they interact with each other in between 750 different ways. So it's an awful lot of different equations that are trying to be solved at the same time on top of this other parts of the sort of weather and climate models. And because of this, it's quite an expensive part of the workflow. And in fact, it typically takes about a quarter of the total runtime of the UM. UM is the current weather model used by the Met Office. And I'm showing a flame graph here of, this is a particular configuration that's most of the UKCA. Within that, there's these three different components for the aerosol code, the chemistry code, and the photolysis, which is chemistry that involves photons, so like light. And the chemistry part is the most expensive. So that's kind of the part that we've been focusing on. It takes about 40% of UKCA's runtime. So I used to work at the Met Office, and I was involved in a GPU port for the chemistry model. And then now that I'm in Cambridge, I'm still working on it sort of in one project and then in a side project as well. So the main issue in this chemistry model is that there's a load of redundant calculations. So we take the planet, split it up into this grid, as was mentioned in the talk earlier, and then this grid is then split up into different chunks in the solver. So this could be either like vertical columns or horizontal levels or the whole thing at once or just one box. Like there's lots of different options. But then when we go into the time stepping scheme, you sort of consider a chunk, and if you want to integrate over some time window, then you will attempt to solve all of the three boxes in the chunk with the default time step of an hour. And in some cases that'll work, in some cases it won't. So for example, certain heights in the atmosphere are problematic, or like points that are over a megacity. There'll be a lot of pollution, and so it's very complex chemistry, it's hard to solve. And so basically, if this happens, then the entire chunk is resolved, even the points that were fine. And then if that happens again, it will, you'll just keep halving the time step until you get a small enough time step that all the points solve. And just to sort of demonstrate the schematic on the right, and then on the bottom right, this is a plot. It's probably too small to see, but it shows the number of times you need to halve the time step for all of the grid boxes. And it's logarithmic scale. So almost all of the grid boxes, you don't need to halve the time step, but there's this very, very small number of points that are difficult to solve. And this was really problematic for the GPU port, because you want these chunks to be as big as possible, but you're always going to have these problematic points. So basically, if you're just going to use this default time step, there's always going to be redundant calculation getting to the time step that you want. And so it would be really great if we could know in advance what the time step needed to be. And so our idea was to use machine learning for this. Like, there's probably other ways to do it, but we thought we'd have a go at trying to predict this with the neural network. So given some input data on what's going on in that grid box in the model, can we predict how many times you need to halve the time step? And this is being done using FTorch, which I'm going to talk about in track A after lunch. If you want to hear more about the sort of story of how FTorch was developed, it's a Fortran interface of PyTorch, which is mainly developed at ICCS in Cambridge. You can see the website and the JOS paper there, if you're interested. It's designed to be familiar to both Fortran programmers and PyTorch users, and it interfaces with the C++ backend that's underneath PyTorch, so that we can avoid data copying. It just basically has pointers to those data structures. And it's open source and open development, as I'll discuss later today if you're interested. So we've got some offline results. So if you remember, almost all of the points you don't need to halve the time step, but in some rare cases you do. And so in the results, preliminary results so far, in no cases, or almost no cases, is the number of halvings overestimated, which is good, because if you overestimate the number of halving steps, you're sort of solving at a smaller time step than you need to. However, in a lot of cases, we're underestimating. And whilst that's not the end of the world, because you'll just go back into the original workflow where you just halve the time step again until it works, it's still not ideal. Like, we want to be able to predict correctly what's going on. And so one of the things we can do to fix this is to generate more training data. And then the other thing is to maybe consider dropping some of the input variables or playing around with those. But the main thing to be concerned about is the fact that because almost all the points are zero, like, there's this inbuilt regularization that, like, if it's pretty much always zero, then the model's going to want to try and predict zero. So we need to somehow account for that in the model. So we'll require some tweaking. So thanks very much for listening. Yeah, just a note to say ICCS is funded by a generous donation from Schmidt Sciences, and this is part of some work that we got some local funding from C2 D3 Accelerate for. Thank you. Thank you.
Yep, looks good for us.
Okay, thanks. So hello, everyone. My name is Tobias. I'm a research software engineer at National Oceanographic Center. I'm sorry for not being in person, but tomorrow I will be in person for my talk. So I will just present a short part of the presentation that I'm going to give tomorrow related to how you can show ZAR data in the browser. And my idea is to show how it can be fast and flexible for big geodata, like data with more than gigabytes of terabytes of size, okay? So just to give a short introduction, so at NOC, we operate global model, global ocean models to predict various oceanographic variables, and these models produce extensive data files with terabytes of size. And since 1 year ago, we start to store those data in ZAR format, and because before that we used to store those data in NetDF and GRIP. And for people that are not familiar with ZAR, ZAR is an open source format for storing chunked and compressed and dimension arrays. And because you can store the files in chunk arrays, so you don't need to, if you want to access the file, you don't need to access the whole data set. If you just need a small part, you can only access the chunks that you need. And because of that, you can also parallelize the way that you access the files, because if you need several chunks, we can access all the chunks in a parallel way. So because of that, it's fast to access that. And you can store the data in the object store. So store data in object store is cheaper. So you can see that ZAR is fast and cheap. And a really good thing about ZAR is that it's popular with the most Python libraries that people use for n-dimensional arrays like NumPy, Xarray, and Dask. But as I said, ZAR is great for scalable storage and analysis. But if you want to show the data in a browser, like in the Chrome, in Firefox, it can be hard, really hard, because the end user expect fast interactive tools, but the existing WebGL and JavaScript still struggle with real-time decoding. And if you want to subset large array of data, it's a pain. Like in ocean models are large array data sets, like with lat, long, depth, and time dimensions. For many years, people used to work using some workarounds, convert data to COG, or work directly with NetDef files, but it's not the best way to do that. So I will show today 2 strategies that we're using at NOC in a project called Atlantis. I will talk more about that tomorrow. But the first strategy is to use a client-side only approach where the ZAR file is parsed in the front-end application. So there's no backend here, everything's on JavaScript. And the second one, we are using a JavaScript, we're using a backend, a tile server in the backend that is integrated with Xarray and just read the part of the file that I need, convert to PNG tiles and bring the data to the front end. Tomorrow I'll show why this approach is better than this approach here. So to increase the performance, we may need to convert the data a little bit. Of course, this is not mandatory, but it's good if you want to increase the performance. So I need to reproject the data, transform the data, so like create pyramids in the ZAR files. So with that, I can increase the performance, because if I don't want the full resolution, I just get the low resolution image. I also need to rechunk the data. There are some papers showing that small chunks is better for web visualization. And then I'm uploading again the files in another object store. So I'll show a live demo here. So this is the architecture of the live demo. If you have any doubts about that, please let me know. And here I have the GitHub repo and the link for the live demo. So this is a React application. So here, the first example that I want to show is the pure client-side approach. So in this case here, you can see that it's really fast. In this case here, I'm parsing all the ZAR files in the front end with using JavaScript libraries. You can see that while I'm zooming in, the resolution is becoming better because it's getting another pyramids file, part of the file. And I can like change the time dimension, and I can edit colors as well. So a good thing about this is that I'm just changing CSS variables on the file, so that's why it's really fast. The second one is using a backend tile server. So in this case, I'm sending a request to the backend, bringing the PNG tiles to the front end, and showing the application. You can see that it's fast as well. I can change the time dimension. So just for an example, this data set has 20 gigabytes, and you can see that it's fast. I can change the color as well. In this case, everything is done in the backend. And another thing that I can do in this approach is that I can bring the data to the front end and create animation. So for example, I'm here, interact with 2 ZAR files, bring the data to the front end in low resolution and create animations. And I can also interact like with timestamps and Z levels, like, yeah. That's it. So if you have any doubts, you can ask me. Tomorrow will be in person, and I'll have a talk tomorrow together with Matt from UKC E8. So I will invite you to come tomorrow afternoon to our talk. Thank you very much for your time.
Thank you very much. Okay, I think we've got one more speaker. I was told that there are some movies and other things as well. So the question was whether you wanted to share your own slides or whether it would work from here.
I'm thinking this.
Okay, then I'll share the screen again. Do you need the slides first?
Yes, please. Yeah.
Okay, it's Dimitrios talking about climate music.
Okay. Morning, everyone, or afternoon now. So this was a small Python project that is hopefully going to be public soon. So warning, there will be some sounds in it. Some of them aren't very pleasant, but then it's a work in progress. And for those of you who can access the docs currently, they were written with co-pilots. Please don't bite me. Okay, so climate music, what is it? Well, it's a Python package that a few software engineers at the Met Office put together to sonify, so to take data and turn that into sound. And that helps you listen to the patterns in the data instead of just seeing it. Okay, so it's a way of making data more accessible. So how does it work? Well, say I have, oh, it's a bit small, but say if I have this rainfall data, 4 data points, this great data set, and I want to convert this to data, I'll choose a musical scale, and then that will be translated into the notes of the musical scale and output by the software as either directly to an audio file, to a WAV file, or if anybody plays instruments, to a MIDI file, so an instruction file for instruments, so that you can give it a nicer sound than just a very robotic sounding beep, 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 beep. So you could put a piano on it, you could put a saxophone or something more interesting. So this was inspired by this work by Lee Demora. So I'll play you some of this briefly because this is the only nice music that's in my talk and it wasn't made by me. So hopefully this will come through. It is long and there are more of them. Oh, not appearing online.
They can click a bit.
They can click on the link. I will put the link in the thing, and I will. Can I stop sharing briefly and share again with sound? Because you'll need to see the next one. Share sound. Okay, perfect. And then go back here. Okay, sorry about that. Okay, so that was obviously a lot of work from Lee, and that used multiple sets of data over Ascension Island, and lots of passing through instruments and making it sound nice at the end. So that takes a lot of work. Okay, so what we've done is simplify this with the beginning process of that on your journey to making nice music. It doesn't produce nice music out of the box. So what does it do? So it can convert time series data, and it must be time series data, straight into WAV files or into MIDI files. and it can automatically process some Met Office climate series data as well. You can add pre-processors for your own data sources in there. What it won't do is clean up your data to make it ready to convert into sound, and it does not convert MIDI files into nice audio like you heard in that YouTube video for you. Why do we bother doing it? Mostly the top one, and then I put the I borrowed this from a presentation we did at work. So the bottom bit is for my manager. It's the learning section, starting new Python projects, using make docs. There's a lot of cool stuff with configuration validation, testing, and the preprocessor sort of pattern. So if you want to ask me about that, then please do, and I will post this example in the Slack to save your ears from it, because it's not as nice as the other one. Cool.
Okay, thank you very much. Okay, I'm now switching over to the slide, and I think Colin, you are leading on this discussion bit. So please, you can still use this. We are in room 04, I think.
04 in track D.
Yeah, track D here. You can see that on the top. You can use that, and I think there's no question for Esther yet.
We have something in the slides.
Hmm?
We have something in the slides for the
I think
discussion session.
just to use the Slido in the Mentimeter.
Yeah.
Okay.
Yeah.
So are we splitting the groups up, people into groups? Was that the
No, that's in the second
That was the second
session. So
Questions.
yeah.
So yeah, this is really just a chance then for us to answer the questions that were remaining on the slide first. So these are in order of upvotes, aren't they? So I guess first we'll go over to Joe on the ML interface for Fortran. Sounds interesting. Are there other examples of it being used, or is this new code for the project?
No, so it's not a new thing. So as I mentioned before, I'll be giving a talk on FTorch and how it kind of came out of project work in track A after lunch. So it's been around for a few years. It kind of came out of two different projects where there was people that had climate models written in Fortran and wanted to make use of ML tools written in PyTorch. So it was developed by people on my team to do that. It has been used by several different researchers since then. So, and we do have a JOS paper as well that came out earlier this year. So if you're interested in using it, feel free to come and chat to me afterwards, or read the paper, look at the.
Perhaps you want to share the JOS link in the Slack?
Yes, I can do that.
Okay, thank you. So next for the Met Office tool, guys, how fast is the transfer between X-ray and Iris objects?
I don't know off the top of my head. I think it's decently fast. I think the design of NC data was to be a pretty base level object, so it's kind of. I think the idea was it's somewhere kind of in between the top level Iris layer and the sort of NetCTF layer, where you kind of have them in between, where it's generic enough that an overlay between Iris and things like X-ray. So I would assume that it's fast enough. I have confidence in my colleague who wrote it. Yeah, couldn't tell very well.
Thank you. All right, so next up for Matt is UEFI-HY. Looks like a great tool. Just wondering why Python was chosen as the basis rather than a lower level language, especially since it seems like you're working to improve performance.
I'm not sure. I don't actually know. Clearly, the project after a lot of it was already done. It was already developed. So I'd probably go with what the original developer was familiar with. Well,
Yeah, what was it?
Yeah.
So we tried Python because the objective of Unify was to make it much easier for people to develop new experimental codes and put them in a coupled environment. So it was designed for ground up to be easy to work with. Now we're trying to make it.
I also sort of maybe question the premise slightly there that Python these days, if you're using things like NumPy as your fundamental libraries, the performance isn't often that different from lower level languages.
Oh, yeah, no, certainly the performance per single thread is fine. The issue is we need to parallelize it, because one thread is not enough.
Brilliant. So moving on then, so Henry, regarding CF metadata support, the IRIS documentation states that IRIS implements a data model based on the CF conventions, but I've not found evidence or this nor been able to find anything in the box covering what the model is. Do you know any more?
I suppose maybe this is just a communication problem on what the expectation of a data model is, and maybe different people have a different idea of what a data model is. I think what we're getting part of that fundamental approach, the way that we designed IRIS from the ground up was in order to make sure that we can cover everything that CF covers. So basically, everything that CF can represent, IRIS is supposed to be able to represent. I think that's what we mean by that, and that has informed the structure of what we're doing. I guess maybe if you have another idea of what a data model is, I'd be interested to know, because if we're being misleading on our documentation, I guess there's room for a discussion.
Okay, and then it looks like we've got several questions for Demetrios. I should also point out that's great. We would also be happy to take questions, I'm assuming, for Brian at this point. It's not just on the lightning talks, and any general discussion points that you want to have. And also, I don't think Esther has yet had a question. So. But first, over to Demetrios. So how much massaging is required to get the music to sound pleasant or in tune, like your first example?
A large one. Outputting directly to an audio file sounds like nails on a chalkboard. So you have to output to a MIDI instruction file, and then open that up with special software and assign an instrument. And normally, massaging is a good word. The notes that come out, because you have a lot of data, right? We all have a lot of data, too much data. We can't just take petabytes of data like we were discussing earlier and turn it into one piece of music. Okay, when you saw Lee Moore's YouTube video, on his time series graphs that came up, you could see the beats, and it was like he was smoothing out the data. So we have a smoothing function in the Python, but you also have to do that afterwards as well. And in some cases, that's like manually deleting some notes to make sure it's clearer what the pattern is.
I also saw in that he had selected Ascension Island. I'm assuming he maybe chose other places first and they didn't sound as good, and that was picked because it sounded good.
No idea. There are other ones which I think are perhaps not Ascension Island on this YouTube site.
And then another question for you is, I'm not sure I follow how the music represents the data. Did you do, or are you planning to do, user tests that verify that people think it is useful?
Yes, we have plans to do more testing. Perhaps I'll put the one in Slack with the climate stripes. That's much more obvious when you listen to the track that there is a trend that you can hear. So it's the pitch, the change in pitch that denotes the change in data, and you can choose whether a higher pitch is a higher value, or for temperatures, I think we've chosen lower pitches, so deeper sounds, that's a higher temperature because it sounds more urgent or dangerous, if you like. But yes, we need to do testing on it. It's not the normal way of showing better data. So.
Yeah, well, I imagine the climate stripes actually sonify quite well. It's just an ascending scale, basically.
Yes, yeah.
Oh, actually, given the updates, we've now flipped order, so we'll come back to you in a minute, if that's all right. So a general question, the Mentimeter poll showed there was a lot of interest in learning more domain knowledge. Does anyone have any good examples of domain area training for RSCs? Anyone want to come in on that? I might just say, actually, at NOC, we sort of did this, that our Marine Autonomous Robotics Systems group started doing some training for their engineers in oceanography, and it snowballed a bit to become something that the whole organization actually turned up for. And we had about, I think, 8 or so basically guest lectures from different researchers across the organisation, teaching us kind of undergraduate level oceanography, and that was really good. But it hasn't happened again, despite all of the sort of non-scientists quite wanted it. I think it put quite a load on the scientists who were delivering it. I wonder if anyone else has done anything similar or managed to get it more formalised or solidly. Yeah.
Well, if it can't work at the map, we have an introduction to meteorology and an introduction to climate course. That is a week-long course that teaches you the basics of meteorology or climate science, and that's actually a regularly run, more formal course, and that works quite well.
So who delivers that?
So that's delivered internally by some of our climate scientists or our meteorologists.
Do you think there would be a way to get that broadcast more widely, like external to the Met Office? Because I think this is something that seems to be lacking from a lot of people's groups, is domain training. And do we need to replicate it if it's already being done really well somewhere?
Definitely an interesting point. So the Met Office College, which is just an internal organisation that inside the Met Office that does tons of training, does do training for people outside the Met Office. They don't run those specific courses, but I'd say it would be possible if there was motivation/funding.
It's always the issue, the funding.
Yeah. I remember this coming up a bit last year and someone sort of said, how do I get into this area when I don't know anything about it? And actually having this accessible to someone before they apply for a job might be a good way of making them a standout candidate when they do. All right, moving on then. Esther now has a question. So is this platform hosted at NOC, and what barriers did you face setting this up? Were there any security issues, and how do you ensure funding for maintenance of the platform?
I'm going to bounce some of it back to Colin. But yes, so our test deployment is hosted at NOC. We're running on a couple of servers that we borrowed from another project. We weren't using them anymore. So our test deployment is hosted internally. We're also testing deployments on Jasmine's on-managed cloud and on a commercial cloud provider. I'm going to send all of the setting things up questions back to Colin, but funding, we've actually taken a lot of discussion. So the money originally came through NERC and Atlantis, but we've had a lot of discussion internally at NOC, and we've actually managed to get overheads on projects increased slightly to fund some of our team to work on sort of this underlying digital transformation work without being project funded all of the time. You can talk about that.
Also, on the funding side, I think there were two other smaller projects that also funded this as well. So there was Class, which was Atlantis' predecessor, and there was another small project with Jasmine that gave us some money. So it has been a bit of a mix and match of several projects. On the security side and the barriers, we had a little bit of a problem between like what should be the responsibility of IT and what should be the responsibility of our team. Fortunately, we have the added advantage that one of our team moved to our team from IT. So he knows IT, he knows what the process is. They were slightly hesitant to actually give us root access on a server that we would actually be able to access people's home directories on, but we wanted home directories to be available. But then they're like, oh, he knows the way and knows the rules, and it's okay because we've got someone who was in IT. I can see that might change over time. We do have to comply with all the same security policies that the servers do. So there are security scans and antivirus software and things like that that we have to install. When we're running something that's external, it's not connected to any of our data stores, so we don't actually have to follow those rules. Although I did realize recently we get security scans through GISC that go to anything with our domain name, even if that's actually hosted by an external provider. So I have had problems in the past where things that were hosted for a project on Jasmine with a NOC AC UK domain name still get security reports for the most trivial things sometimes, and we get told we have to fix them, despite there being almost zero chance that those could actually exploit anything of any use to anybody. I think that covers that. So moving on then to Brian. I'm a big fan of X-Array, Dask, and ZAR for lazy data ops, and it has a large community backing. Would there be a reason to adopt Pi5 backend if I need these features?
So I did answer on Slack, but the brief answer is that if you want to keep doing that, that's fine. What we're doing is offering an opportunity to do it with next if in the same place where the words are.
Okay, thank you. And then I think we'll do the final two for Dimitrios, and I think we'll then be at time for lunch. So one more, would weather music just be very slow tempo climate music? Discuss.
The tempo is set by how many data points in your time series you'd like to play per second. So would weather music just be very slow climate music? Yeah, it's up to you. You can pick the tempo. And then I haven't heard the second one, but I know NASA and other people do lots of sonification of their stuff. And then using this in outreach, we need to go through the testing.
Okay, so welcome those of you who are here beforehand. So there are a few different links associated with the session, which will be on some slides, but if you look on your tables, there should be some nice QR codes, web links explaining everything. I believe we're using the RS Econ Slido, so hopefully you know where that is already for any questions. We've also got a hack pad up there and a few other resources. So this is a continuation of the inaugural Geoscience Special Interest Group meeting. So we gathered as a community last year and set out the foundations of what we were hoping to get. And then this is the first year we've had sort of a proper meeting. It's being headed up by Helen and Isabel, who are here, along with other members of the committee who are supporting it. We're going to start this session off with another keynote. This time round, we've got Andrea Sharp, who is the head of digital infrastructure and data at NERC, the Natural Environment Research Council. So please, over to you, Andrea.
Thank you very much, and thank you very much for the introduction. And just firstly, apologies, I can't be there in person. So I was asked to present something on the links between data, digital research infrastructure, and the role for research technical professionals. Now, I'm not a research technical professional myself, so I really wondered what I could bring that would be useful to you. So what I'm going to talk about is digital research infrastructure, a bit about the evolving landscape, the direction and ambition going forwards from a UKRI perspective, and then focusing down on environmental science. So before I do, I just think there is a lot happening in this space and it's evolving at a really rapid pace. And so when considering the digital research infrastructure, it's really useful to understand the complexities and dependencies on the developing digital research infrastructure ecosystem. And this can be done by this sphere of influence. So if we look on one side there, we've got the HM government, and so they are making decisions on large digital research infrastructure spend. And we've had the announcement of the 175 million supercomputer, which will replace Archer 2. And then there's the AI research resource, which was funded as well, and that's already been mentioned a little today. Then on the other side of that circle, we've got the UKRI Digital Research Infrastructure Programme. And for us in environmental sciences, it's about how do we collaborate and influence this to make sure that there is a fit for purpose, coherent programme that sits across UKRI. We're also working with partners, so for example, the Met Office, and thinking about how we can use that digital research infrastructure. And then in the middle there, it's about, what can NERC specifically do for environmental sciences? So, and I'm sure a lot of you are familiar with these. So, government are embracing the use and application of critical technology, and there's a lot of focus on economic growth and the use of AI in helping us to do this. Now, there's lots going on in this area, and these three documents that I presented here were all published this year in 2025. And so there is lots of opportunities being put forwards and a lot of the changing landscape. So we've got that AI Opportunities Action Plan. In the middle there, we've got the Science and Technology Framework. And within this, the government set out the ambition to deliver change and improve lives for citizens. And to achieve this, there's the mention of unlocking the full potential of UK science and technology to drive growth, create jobs, and ensure all citizens live healthy, secure, and sustainable lives. To enable this, amongst other drivers, there are investment in R&D, but also talent and skills and the research and innovation infrastructure. And this isn't just the infrastructure itself, it's thinking about the dependencies, technological dependencies, and also access to data. And I've just put a quote there from the Right Honourable Peter Carl, who's the Secretary of State, down the bottom there, about data being the DNA of modern life and quietly driving every aspect of our society and economy. Unlocking the value of data isn't a new thing. So in the National Data Strategy, which was released in 2020, this was mentioned. And of course, we've had the announcement for the National Data Library as well. I think now it's really about having that right infrastructure and including software infrastructure to be able to really pull through the use and gain those insights from that data. So most recently, and this was just at the beginning of the summer, there was the launch of the UK roadmap, and this was between DCIT and also UKRI. Now, this really just illustrates how essential compute is to modern day science, and it also really sets out some of that evolving landscape. And I've mentioned the announcement of the 175 million supercomputer, but also within this roadmap, they mentioned the national or the aim for national supercomputer centres. Within the roadmap, it talks about a vision for building a platform for science, innovation and discovery. This isn't a platform as such, but it's about building an ecosystem of diverse joined up compute that's able to serve the needs of the scientific needs, but also innovation life cycles. But it also acknowledges that to support AI and science ambitions, it's not just about building that compute capacity, but also deepening national capacity across software, skills, data, and user support. And if you haven't read it, it is worth a read. And you could just flick to the end where actually they set out some of the proposed plans for the compute ecosystem, including around software. So the UKRI Digital Research Infrastructure Programme. This programme is looking to bring together the councils across UKRI to create a federated, interoperable, interdisciplinary portfolio of digital research infrastructure. And the vision is for a seamless connectivity between data, access to tools, techniques, and the skills to be able to undertake ambitious and creative research. If we look at the approach, it sets out the definition of DRI, and it is much broader than just the physical infrastructure itself. It's thinking about that large-scale compute and the data infrastructures, but also the software, the networks, the toolings, and the skilled DRI professionals. The programme itself is working to address challenges around fragmentation of DRI between and across disciplines, and creating a more interconnected, open, inclusive, and user-friendly infrastructure. This, of course, will involve fostering community engagement and promoting creation of federated infrastructure and ensuring that the DRI funding addresses technical challenges of operating across different disciplines. If we look at the side there, you can see that it's not just about that physical infrastructure, it's about that human DRI. So really recognising that people are crucial to the DRI. They're building it, they're maintaining, they're the ones that are upgrading it. And so actually we need to consider the careers of those people and also supporting their professional development and ensuring that we have that diverse skilled workforce across DRI. It's also about fair DRI, ensuring that the research infrastructure is easily accessible, interoperable and reusable, following those fair principles, and also about sustainability, ensuring the long-term health of the DRI by addressing efficiency, security, environmental, financial challenges to create a sustainable ecosystem. Now the themes, and these have changed slightly, these have evolved slightly. The current themes are around data infrastructure, compute ecosystem, software, and the federation and underpinning tools and techniques. And common across all of these are the skills, so the training, but also the skilled people. And there is a portfolio of projects within this area that have been funded, but I've just pulled one out here, and this one is the Digital Research Technical Professional Skills Network Plus. This is a 9.5 million programme over 4 years. It started this year and has funded 5 projects, which together aim to bring together the disciplines, the sectors and domains across UKI's remit to address cross-cutting challenges around digital RTP skills and careers. And why am I mentioning this one specifically? It is NERC-led, but that's not the reason I'm mentioning it. I'm mentioning it because this programme has a flexible funding pot, which means it will be able to launch calls and there will be some events and there'll be some support for training to further development skills and careers of RTPs across the different disciplines and domains of UKI. So moving to environmental sciences, and for fear of boring you all, I'm going back to the NERC digital strategy. And this is, I suppose, getting a little bit old now. It was launched in 2021, but it set out the ambition for digitally enabled environmental science, and we are still working on that. The reason I'm putting it up is really, it's this wheel. It's about this, the real digital ecosystem and the need for that interconnected digital research infrastructure to enable this to happen. And that's thinking about, from the top, from that data collection, the data stewardship, the analysis, the modeling and simulation, and having that infrastructure in place to enable that interconnection, to really drive that through and pull through actionable data to be able to make digitally enabled decisions. And so I've just put this in quickly just to really illustrate some of the thinking that's going on within NERC itself. And we earlier in the summer, we launched the Forward Look, and this sets out the research and innovation priorities over the next 10 years. And there are 3 broad priorities. It's about delivering growth through the use of environment and environmental information, thinking about how we ensure a transition to net zero that benefits everybody, ensuring society is resilient to environmental change and the impacts of that change, and also supporting emerging industries and enabling smarter regulation. Now, to meet these priorities, we cannot do this without the enabling capabilities. That includes the data, whether that's autonomous collection, whether that's in real time. It's about that more accurate modelling and prediction. And that's something that Brian touched on earlier. And it's also about having that, the infrastructure to enable that to happen, but also the skilled workforce, having the diverse skills across research, innovation, and the technical professionals, which combined will help us to gain new insights from the information and actually be able to address those priorities. So what are we thinking about? We're thinking about how do we link up the dots? To be able to really address those priorities, we need to be able to have this integrated DRI ecosystem so that we can get ultimately actionable information and insights from the environmental sciences and the data that it generates. And I can't stress the importance of all the elements of the DRI ecosystem to enable that to happen. And of course, the skilled people. So some of the considerations, what are we actually thinking about? So there's the compute, and I think Brian mentioned it as well, and I've mentioned it earlier about this changing environment for compute. There's going to be different architectures coming online. There are already different architectures online. So how do we really make effective use of that? This will present challenges for the community, and there is some work that has been done, but there is more to be done. And there is potentially some funding coming through that national compute programme. We also need to think about the connections to analysis platforms. So thinking about Jasmine, and Brian touched on this as well. So how do we do that with some of that new compute as well? And obviously it's not just limited to Jasmine, but also then thinking about connections to data science platforms. And it pleased me that these were also mentioned earlier. But then also thinking about the data, and it's about, having that fair data, that should probably be fair DRI, but also thinking about new approaches to data access so that we can really fully use or fully realize the use of AI and putting in place different delivery options to the ones we've had before. This is starting to happen in the EDS, so the Environmental Data Service that NERC funds is starting to think about that. We're often not working in isolation, so we need to be able to share data. We need to be able to work with it. Someone mentioned data wrangling. I think I saw that when we were asked earlier about some of our key expertise. And it's also about the ability to, to really get that insight from that data. So how do we apply data science techniques to be able to do that? There are platforms out there. that could help us to do this, but we're thinking about this specifically for environmental science needs. And these research environments, and I think Esther touched on this as well, is really about, they're about software and really about software as an infrastructure. I have another slide in a moment about data spaces, which is something that is being thought about. And we are developing a concept called the Environmental Data Research UK. And this, I haven't put this up there here specifically because it's not currently a funded program. It's a concept that we're thinking about, and that is really thinking about how do we link up the dots so that actually we can pull together different sources of data and information, that we can apply those data science techniques, and that we can then actually get actionable information from that data to address some of those priorities we need. And one of the ways that we're thinking about doing that is through a research environment, through implementing a research environment, or thinking about a data space. And that's something that's a concept that's being talked about in Europe. And so I'll talk about that on the next slide. Before I do that, I just wanted to really emphasize that, research technical professionals are so important throughout the digital research infrastructure, and their role will be key in enabling us to further develop that and to really then drive forwards things within environmental sciences. Before I finish, I'm just going to touch on data spaces, and this is something that we're thinking about, kind of whether it's research environments, data spaces, but basically within Europe, they're using this definition for data spaces, and this is an interoperable framework based on common governance principles, standards, practices, and enabling services that enables trusted data transactions between participants. And a lot of this, it is about software and putting in the right frameworks. And the development involves that implementation of the software and the services, and this will enable participation in the data space, the federation of services to enable interplay between the participants, and also the creation of value creation services. So thinking about the data science techniques and being able to then apply those to the data that is being looked at within the data space. So there are some current examples, and Dare UK is a UKRI funded programme. This is specifically looking at federating trusted research environments. So it's looking at sharing sensitive data. And so this is primarily being done within the MRC and the ESRC area. And it's within that programme, they're considering the access to data, the governance required, the security around that data, and the platforms that are being developed, but also then thinking about the application of tools and being able to gain insight from that data. They're also thinking about whether it's possible to have temporary trusted research environments, and thinking about the, how that software and making sure that that software is platform agnostic, so it could be moved around. Within Europe itself, there is the data spaces, and there's a data spaces support center, and they have produced a blueprint for data spaces. So I just put that there in case that was of interest to anyone. So in summary, the DRI landscape is really complex, and to really fully utilize it, we need to be able to connect that ecosystem so that we can then use this DRI ecosystem to address some of those key priorities that I set out. And that's the priorities both for NERC and also for government around growth and around their missions. And thinking, and then within that environment, it's just emphasizing that importance of the research technical professionals in both the development and the evolution of the digital research ecosystem. And so I suppose turning it around and just setting out a challenge for the Geosciences SIG is thinking about what are the barriers and opportunities to ensure that geosciences can fully realise the opportunities presented by DRI. And that is where I was just going to finish.
So on the ones that I can see at the moment, you spoke about the transition to net zero. Is that something that you're looking at specifically within NERC, or is that something that NERC is leading sort of an initiative in across the research councils in the UK?
So I think that's both. So there is a digital research infrastructure funded program that actually NERC is leading, and that's called NetDrive. And I can provide links that could be sent out after this if that's useful. And that is looking at and thinking about you know, what do we need to do within digital research infrastructure to try and meet net zero? Obviously, there are some huge challenges with some of the new compute that's coming online, but that program is looking at that, and that's pulling together. It's got some champions, and it's pulling together networks to see, you know, what could be done there.
Super, thank you. You talked a little bit about efficiency and green compute, which often focuses on kind of high performance computing. Have you thought about improving how NERC researchers are using desktops for development in more efficient ways?
So as part of that, it's part of that Net Drive program actually. So they're not looking at just for NERC, but they're looking across UKRI, and part of that is around the research culture as well. And so it's about how people approach the use of HPC, or how the people approach the use of different types of compute. They are talking about, you know, whether we should be including our own personal PCs as well. And so actually that will come as part of that, part of the research culture piece that they're doing within that program.
Super. And then hang on, it's moving. So I think there's probably time for one last question, but we'll move the other ones over to Slack. So the last one is, you talk about research technical professionals. Who do we need to consider under this umbrella, not just RSEs? And what are the plans to train these technical professionals in the future? Which I guess links to one of the other ones that asks, in the past, EPSRC and STFC have had RSE fellowships. Do NERC have any plans to do training like this or support like this?
Yeah, so you're right. So when I say research technical professionals, I'm not just referring to RSEs. I'm using that as quite a broad brush. So it's, you know, RSEs, it's also data stewards, it's also thinking about that broader range of research technical professionals. So we have been thinking about what we can try and do within this, and we're also talking obviously to UKRI, DRI about what you know, what skills and what we need to do. If I'm being completely honest, from an perspective, I would love to run something like EPSRC have run. We've been discussing that. There is no current plans to do that at the moment. It's something that is in discussion, but it's also for us, it's influencing that DRI research, the DRI program, because they are thinking about the skills and thinking about what could be done. And then also UKRI centrally, so the training teams within UKRI are thinking about the skills and thinking about, you know, what skills are needed across the whole research piece, and not just for research, but also for those research technical professionals. And so it's thinking about how we can work with them and influence them, and make sure that we do have programs that are suitable for everybody.
Super, thank you very much. Like I say, the questions we didn't get to, I believe Helen has been moving over to Slack space, so we might get around to an answer over there. So moving back to keep us roughly on track. Next up, I believe we have the breakout sessions, which I'll pass back over to Helen to talk about.
Okay, so we've got a set of points that we thought might be good to discuss. I think probably form, I don't know, about 5 breakout groups of 10, or groups of 8 to 10 would make sense. So if people can arrange themselves, and then I think have we only got Andrea online? More people have joined. More people have joined. Okay. So if we've got enough people online, we'll put all the online people into one group. Otherwise, we could use the OWL to put them into a hybrid group. Okay, and then we'll give you 20 minutes to discuss these questions, and then if I can get you to assign one leader from each group to write notes from your discussion in the HackMD, and then afterwards we'll have a 15-minute opportunity to give feedback from each group before a broader discussion. Okay, great. If I can get you to maybe push some tables together or stick closer to each other for discussions.
All right, I'll still do 2.5 minutes. Okay, so we start with this table. We'll go 1, 2, 3, 4. So 2.5 minutes for this table at the back. If the lead wants to have a discussion of these 3 questions, any of those 3 questions.
Okay, well, ignore the last one. Let's talk about it. But the first 2, we first went over whether we're talking about success personally or success for your organisation or project, and that we consider those are probably different things. There were a lot of discussion about outputs being a good measure of success, whether that is producing a GitHub repository, producing paper, documentation, things like that. And then we also went into a bit more detail about how it's actually the usability of those outputs. So it's not just that you've produced a bit of software, it's that there are people actually using that bit of software and are able to use it usefully to help themselves. So then we went into a bit more of the overall context of that, so funding deadlines and basically meeting promises that have been made as part of grants and that kind of thing. And yeah, summarised it by saying success is more than just clocking in your daily hours. You've actually got to be producing useful results. On question 2, this was the career progressions. We talked about various pathways that have existed from the relatively structured progression system that exists inside the Met Office to the slightly more ad hoc in UKCEH, largely due to the smaller size of the RCT Met. And then, so the Turing Institute also had quite a formal pathway that gave you a very clear vision of where you were going. For universities, it was a lot more fuzzy, and often you were ending up having to write your own job description for the role you were trying to move into, which had benefits in that you could write the job description for the job you wanted, but it was a lot slower because requirements would always be changing, and you kept having to convince people, and that person might change. So, yeah.
Perfect. 2 minutes, 10 seconds. Brilliant. Right, table 2.
We only tackled one question, which was the career progression one. We talked about an almost ideal thing that was coming from UCL, where they have a junior to standard to senior to principal. So what's the next one? Is it head of, team lead to head of RC? How that's probably the one that most places would, or most of us would like to see everywhere else, but isn't quite what some places have, and some places it's very far from having anything like that at the moment. At NOC, we actually have a somewhat flexible promotional scheme where you can choose which job family you're actually assessed against when you go for promotion, which is often the one that falls to RCs. They don't know which job family to stick you in, and you end up being assessed against things that don't match your job. We also talk about what people do in more senior roles, and whether they are more technical roles, whether it ends up being you spend more time in management, and what happens to those who don't do so much management, whether you can actually get promoted or not, whether that's what people do, just want to do technical things. But we sort of get a few examples of people who have been successful, who have done quite technical things where they become very involved in a particular community, or they're key maintainers of a piece of software, and they end up in very senior, like principal RC type. And also, people do end up doing more managerial work, need to managerial training, and that isn't always able to do, and they don't actually know how to be. But it was pointed out there is the new discourse, the RSE network that is being funded recently, that will hopefully help towards. Does anyone else want to say more to anything that I can cover?
All right, super. It's less than 2 minutes. All right, table 3.
So we mostly focused on the third question, training gaps for knowledge. I'm going to slightly restructure the sequence that we talked about, but we covered like people who come from a computing background often find they have science or maths training gaps. People who come from a science background often have computing training gaps. And you can also sometimes find particular skill sets. So you know, a discussion about DASC, and there's a big training gap there. It'd be quite useful to know more about that, because that seems to be something that people are getting stuck on. And then discuss ways to try and fix some of these. So one company, I think it was not, had an in-person support day, which allows people with a net office. I think you do, but it's not as successful. They have an in-person support day, which allows people to come and learn, but also allows them to disseminate the things they've been developing. So we've got this cool new tool, why don't you try using it? Discussed that the SIG is actually not a bad way for people to find out about other people with useful skill sets. Talked about the fact that SSI, sort of the Sustainability Institute, ran a mentoring scheme a few years ago, which linked PhD students from non-computing backgrounds with mentors from computing backgrounds and provided support for a few months, which might be something to consider. And then I thought to get about how we can increase communication with institutions. That's a bit, people know this stuff, it's just another institution how to find it out. So we really have answers. But yeah, and then we spent about a minute talking about how to measure success and decided it was mostly GitHub merges, PRs, moving things from the columns of the Kanban into done. Yeah,
Brilliant. Thanks very much. All right, table 4.
So we mostly talked about the first one, how do we measure success? And we mostly talked about it from the level of the project of, say, the team. So there's always the good old you can count the number of active papers that you supported or wrote, but as we all know, that only applies to specific projects, or not so much for software or RSC adjacent projects. So you have different avenues that we talked about, but basically none of us could, no supervisors, define a very quantitative, magic, formal way of assessing success. It was all very somewhat simplistic. So we talked about trying to get feedback from your stakeholders or clients, whatever you want to call them, to make sure that you met the requirements and what they were expecting from you. We talked about maybe running some more Scrum Agile style perspectives. So there's more informal discussion with the team more regularly, where you can try and figure out what can do it, wrong, what can you do better. And we, so that's what the application has said, it's also sometimes good idea to try and define success before you actually try to measure it. And so one example that she gave us was trying to, for instance, devise or come up with a survey. So if you try to manage to actually come up with the questions that you want to ask, maybe beforehand and then maybe more importantly after the project, to try and measure success and success as well. Not obviously, but that can really help. And then you can actually really use that quote unquote evidence, for lack of a better word, to back claims that you would do for maybe more resources or more funding. Anyway, just trying to explain that your project was successful and you should be honest.
I'm going to stop you there because that was 2.5 minutes and we are out of time. So thank you for that. Right, am I handing back to you? To me. Okay, perfect. Thank you.
So in the last 15 minutes, we have what happens next for the SIG. So just briefly, what we've done so far, this time last year, we had a weather and climate birds of a feather session here.
And as part of that, we decided we should set up a SIG special interest group as part of SOC RSE. So February this year, that was officially approved. If you go to the SOC RSE website, you can find the links from there to our founding constitution, which sounds wonderfully posh, and the website where there's a bit of detail about what we are. In May, June this year, we had elections and Helen and I were elected as the official chair and deputy. If anybody else wants to be involved, there are more positions open. And there's also a standing committee, which is just people who can come when they can make the meetings, who help run things, help organise stuff like this. And then obviously we get to September 2025 and we're here. So the question is, what comes next? Given we have a group of people here, what would you like to see from this SIG going forward? So, thoughts on this? We're planning an online seminar session in the early spring. This is still in the planning stages, but there'll probably be a couple of hours, depends on how many people want to be involved. And that will be a chance for people to give maybe 15-minute talks around a set of topics. If there's lots of demand for that, we might run it over a few weeks. If it's only a relatively small group of people who want to talk this time around, we'll keep it shorter. But then, yes, what else would you like us to see? This is going to be open discussion, put it on the Slido or run it through. But yeah, work out, it depends on whether I can get somebody to help me put the Slido thing up. But yeah, so think possible things you might want to talk about. What events should we be running? How do we, we talk a bit about knowledge sharing, domain knowledge. Is that something you have ideas about how we could do it? If we do that, then how do we stop it getting out of date very quickly? Because stuff always goes out of date. And then, yeah, suggestion ideas here. Put them in the Slido. If you have ideas and you don't have a chance to put it in the Slido, put it in the Slack for this, in the RSECon 25 Slack. There's a Geoscience channel, which you've probably mostly found by now, but you can put things in there if you think of them over the next few days, and we can then use that as planning to help us move forwards. So yes, we got any, we have suggestions. Okay, good. So I'm not going to answer all these questions, by the way. I'm going to leave it open to the room in some places, because I have no idea whether people are interested in more in-person networking events or more interested in virtual talks. I mean, we can have a show of hands in this room who would want, you're allowed to vote for both options, who would want in-person networking events in this room? Most people. Who would like virtual talks? Slightly different subset, but also most people. Okay, so that sounds like both. And I guess there's then a question of how many people would come to an event that was run outside of RSECon if we ran an in-person event at another time of year. Show of hands, would people potentially be interested in coming to that? Well, of course, yes, money and timings and everything else, but hypothetically.
Where is everyone got region
So from the groups that we were chatting to, Met Office, which is mostly Exeter, NOC, which is Southampton, group in London, we have Bristol, we have some from further north.
I'm afraid NOC is also Liverpool.
Is it not also Liverpool? Oh, right, okay, I didn't know. It's got two bases. So yeah, there's quite a large spread, but it's, am I missing lots of northern people? Are there lots of northern people in the room that I don't know about? Scotland? Yes. Scotland? Scotland, yes. Yes, okay, you're running away, but yes, Edinburgh.
English and skills, so I'm not sure.
You'd be welcome. You're always welcome. Okay, so comment that gathering case studies and how to use available software would be really valuable. I mean, yes. Does anybody have suggestions of how we could do that? I mean, we've got a website, so we could just invite people to post things in the SOC RSE Slack channel, and we could then put them on the website if people would find that helpful. I'm happy to start doing something on that, but it's going to be open to people, like suggestions of what you'd like to do. Enjoyed the lightning talks to hear about projects and things going on. I'd love to have a virtual session with more of these. We're glad to hear that, because we're planning to have a virtual session with more of these. So that's always a nice thought. Yeah, some more in-depth technical talks. So I have a question for in-depth technical talks. Do you reckon we can find a single topic that lots of people would be interested in? Or do we all have different things that we'd like to have in person, like something? So does anybody have a suggestion of a topic that they think would be popular for that sort of technical talk?
Handling your big array data.
Yeah, would people be interested in something like that? A few nods around the room.
I guess the question is other people who are interested in that.
Or at least how many people are really not interested in that and wouldn't turn up, yes.
My experience with fancy library X.
Yeah.
Fancy data format. Visualization is always a fun one.
Mm-hmm. I'm making very detailed notes here on the phone. Yeah. You're taking notes as well, good. Would blog posts on the website be useful? E.g., I wrote this bit of software to do X, followed by, would people be willing to write blog posts for the website? Because hypothetically, yes, but I'm not going to volunteer to write all of those. So,
like sometimes people write internal publications for their own organization, right? To like share on intranet, and like obviously sometimes there are permissions problems, but like we could put some of those, like basically take some of those as written and publicize them on the Geoscience SIG website. Yeah.
So it sounds like having some more space on the website for a range of like, here's some tools that we've been developing. If you're interested, come and look at these. Would be useful. Would it be useful to compile short intros for group members? May help identify areas of expertise.
I think this is a brilliant idea. I think a lot of the like regional groups and stuff will say like who's involved, but then you don't know who's involved. Like, you know, the institutes are involved, but you don't know like who's part of it, what they're interested in, and that's a brilliant idea.
Yeah. So the challenge is how you maintain it. I think it can be done. And we could use this if we have once a year meeting here to refresh things. So we could say once a year, let's see who's still involved. Let's see if there's anything, sort of poke people once a year to check that they're still active in it. I don't know. Anybody? Yeah, and link your GitHub repos, and then people can see what's going on. A GitHub repo pointing at useful resources. How would we set that up? I mean, having a set of useful resources definitely would be helpful. How we would create it, whether it would be on, because we right, and then having a wiki. Yeah, I'm trying to work out a page on the website. I was wondering if just having a page on the website might be the equivalent. But yeah, I think it would be helpful to have that. And again, how we build that, ask for input from the community, check it once a year, sort of thing. Yeah. Might be a way of keeping on top of it. Because I agree that a lot of the time you can get very excited to create all these resources and then they just sit there and 2 years later they're useless. So it's trying to keep something maintained. Any final thoughts? We've got 5 minutes left.
I've seen that there's RSC London are running the bite-sized RSC sessions where they sort of do 1 hour, 1 hour and a half on certain topics that are useful for the whole RSC community, which is the Geoscience bite-sized RSC. On the slide, they mentioned gas.
Yeah.
We have a half-day course we've written about gas as one of the sections. Probably extract that as well.
Sounds useful, yes. Okay, so are you volunteering to do this? Or at least talk about it, yeah. So we can discuss it. Because yes, I think so. Online seminar could be people just presenting their own work, but we could also do equivalent online training things. Here's something we think you're interested in. Online is probably easier than in person if it's only an hour, because your conference so far for you.
Yeah, it's not worth traveling from Boston.
No. Even if the networking's less good when you're online, but still be done. A logo. Does anybody have capability to design a logo in this room? It also gets a bit technical, so it has to be signed off by SOC RSE, I think.
Could we do a logo competition?
We could do a logo competition and see if anybody is.
6 meeting slides.
Right.
Then actually has been modified slightly by society.
Yeah.
And that's what trade well.
Yeah. Potentially. Okay. If anybody, we can see if people are excited to create a geoscience logo, because it would be fun to have, and it would be nice to be able to put it on the branding of stuff we do. Any final thoughts, or should we wrap up a couple of minutes early to give people a chance to get to the next session? I think probably that. There is there? No, it's straight to posters. Yeah, okay, in which case I think we will call a halt now and say thank you to everybody for coming. Thank you for all the ideas. Oh, thank you, yes, I can say thank you. And I will continue to raise this. So yeah, we'll continue the discussion on the online Slack channel.
Oh, yes.
So that should be good. Yes, you're now free to go. Thank you.